Right, good morning. Welcome back. First things first, you'll notice today looks like the previous days. This is no longer a weird day, so that's something. The day is yet young. Who knows? Who knows what's coming next? But thanks for sticking with last week. Something came up, and totally unexpected, and in good news, this particular unexpected thing is not possible to come up again, so that's cool, or something. And yeah, let's just keep ourselves moving forward. We did not have any sort of assessment last week, in part because I was more or less unavailable. And all right, let's just do our thing. Yeah, this is going on YouTube. I'll give you more details in class. Maybe. I'm not sure. I don't know what kind of detail you want. But we're here. Right, here's what I do know. I've been planning this for weeks by now. So today and tomorrow we'll do a bunch with elements groups. On Wednesday, I'll show you some about trends. This is the groups and trends unit. So, we typically think about, one question that I will often pitch and can pitch now also, is as you go through these and are learning about the different groups and what they do and stuff like that, the question of if you were an element, which group would you be a part of? And just kind of thinking about these are ways that elements tend to behave. And at this particular point, now that we've gone through an excessive amount of electron configurations, we'll pull back some of that into understanding how electrons influence group properties. The sun rose. You can see the sun rising on the paper. That's cool. Okay. Yeah, so different groups of elements have different properties based on their electron configurations. That makes sense. Okay, so let's just go ahead and jump in. There are 8 groups, and you each researched one group, and you will watch this video and also the 8 group videos between Monday and Tuesday this week. So if you are taking the ACT, you've got extra days. So just if you are taking the ACT, think about wrapping this up by Friday this week. If you are not taking the ACT, try to keep yourself on track, because that'll just be easier overall. Okay, third time's charm, jumping in. Groups of elements. Groups of elements. We learn about 8 groups. There are lots of different ways to divide up the periodic table. Without going into too much detail, you may see it printed even in different ways. There's a semicircle method. There's the method with helium over by hydrogen in the S block. So some things can change, some things just don't. The semicircle method is putting the inner transition metals where they actually belong, instead of in those 2 rows underneath. We're doing 8 groups here because a full valence shell in the SNP orbitals is 8 electrons, but that was a little much. Okay, here we go. I'm going to do these in color. This will be the day that you will color in your periodic table. Group 1 is over here. You're going to see some patterns on where these things are located. You are invited to draw yourself a little outline of the periodic table. I've done a billion of these. If yours look different, that's totally cool. The main thing here is that group 1 is here. Group 1 is the alkali metals. And group 1, so this is the name, the location and the name. I should say, before I jump in, watch this video either before or after all of your friends' group videos. Preferably watch theirs first and this after. The student presentations will fill in, like, will do lots of, like, the bulk will come from the student presentations. This is going to fill in some of the electron structure type stuff that we had not covered by the time you made your presentation back in whatever week that was. Okay, so alkali metals, I'll do a few properties, but you'll get most from your student presentations. Alkali metals are very unstable. And specifically, this group of elements tends to explode, blow up, explode. Especially on contact with water, especially in water. Okay, so your group 1 group may or may not have, you know, and there's good reason if you didn't, but you can look up videos of your alkali metals blowing up. I can link you a video of all sorts of, you know, they put a gram of metal, which is like a paper clip is a gram, so like the amount of metal in a paper clip, or maybe 2 grams or something like that, not very much, into a bathtub of water, and it will do wild things. I can show you some of these. Interestingly, so this is all true. Also true is that you see these in your food labels. Sounds great. Food labels. Okay, that doesn't make any sense. They tend to explode on contact with water, and yet you are primarily made of water, so how is it that you also eat them? And your student presentation might get into this, but this has to do with, they have a stable form. So as, we can even add this, very unstable as atoms. But they have a stable form that's similar to their atom form, but significantly different, because the atom form blows up, but the stable form also exists. If you rewind your brain to like the 2nd or 3rd day of the class when you're at that story of an atom, you've already written about the stable form, the most likely form an atom will take if it changes. Molecule is the other option, but the other one from that, protons, neutrons, electrons, the easiest one to move, the one on the outside. If we move that type, the stable form has to do with gaining and losing that easiest subatomic particle to gain or lose. That'll be your preview. That'll be all that we do next week, is talk about that. Okay, right. Both unstable and in food labels. Oh, structures. Okay, so Lewis structures. Remember, Lewis structures is shorthand, so that's cool. Your alkali metals include things like sodium and potassium and rubidium. That one doesn't show up in food labels. It's less common than sodium and potassium. And also, these are super important for your nerves. But let's not go into biochem right now. But if you asked for biologically active metals, this is how your brain works. Ta-da! Okay, this is also very important. Let me know if you want a giant tangent. That could be an entire course on how your brain works. Okay, Lewis structures, and then Aufbau. And sorry if you're like, I never want to see another Aufbau. Let's do these in core notation. So something like sodium will have a core notation, Aufbau, of, it's got that neon core, and then 1 electron in its s orbital. Whoa. Potassium has got that argon core. I should probably get my table out rather than doing this to remember. Yep, argon core with 1 electron in its outside shell s orbital. Now you may notice that in our Lewis structures we've got 1 valence electron, and in our Aufbaus we've got 1 electron outside of our core. It's the same 1 electron. And it's that 1 little electron outside the core that moves to form ions. I'm just going to give you this. Once this outside electron is removed, then the structure of the leftover ion is just this core. The core is really hard to break and very stable, which is how you get in atom form with this outside electron still there. Super wants to get rid of this outside thing. That's where it's going to blow up. Once it's blown up, it's never getting that outside electron back, ever, because it's way more stable without it. In its stable form, this ion, after we've lost that outside electron, that stable ion form that is just that core, is how you get the sodium ion being the, the conducting power of your neurons. If that was all like super wild, don't worry about it. We'll get back to stuff like that with ions. Feel free to rewind. I'm not gonna do it like hash it a ton, but yeah, it's kind of cool. Things that blow up and then become like very stable once they're in their blown up form. Okay. Interestingly, a similar type of thing happens in group 2. That does not look like a different color. Maybe this will look like a different color. Yes, that looks like a different color. Group 2. Okay, so group 2 is actually fairly similar to group 1 in lots of ways, and dissimilar in other ways. So group 1 was this first column over here. Group 2 is the second column. So far, so good. First column is group 1, second column is group 2. That makes sense. Also, fun facts, group 2's name sounds a whole lot like group 1's name. I'm going to put them both on the screen at the same time. Group 2 is the alkaline. Okay, this does not look like a significant difference yet. Alkaline earth metals. Okay, and things that might help you remember like the difference here. Your alkali metals, alkali is 1 word, that's group 1. Alkaline earth is 2 words, that's group 2. Okay, so they really are similar to each other, groups 1 and 2 in a lot of ways and different in some other ways. Okay. And you'll notice right off the bat that group 1 and group 2 are the 2 groups in the S block. And that makes sense here also. Your Aufbau structure has 1 electron in the s orbital. For alkalis, 1, group 1, 1 word, okay. Group 2, let's just go with structures because I happen to be talking about structures. Lewis structures. For group 2 are things like, magnesium, and figure these out like anything else. Oh, here's my real table. Let's use this. Okay, so magnesium. start from the side, count across, 1, 2, 2 valence electrons. Let's just do all, so group 2 is the second column right here. Any element that you count in group 2, since it's in the second column, is going to have 2 valence electrons. So magnesium, 1, 2, calcium, 1, 2, strontium, 1, 2, etc., etc. And so in all of our Lewis structures, these have 2 valence electrons. Magnesium has 2 valence electrons. Calcium has 2 valence electrons. I'm just going to choose another one just to go nuts a little bit. We did, okay, whatever. Barium, but if you were looking at your table and you chose strontium or iridium or beryllium, those are all alkaline earth and they all have 2 valence electrons as well. I tend to do 3 Lewis structures so you see the pattern without like making you write all of them. If you're writing these with your valence electrons on different sides, as long as you have them on 2 different sides, does not matter which 2 sides. If I was doing this in pencil, I would put it in different sides to show you that that's fine. You don't have to do like left and right. You can do top, bottom, top, right, top, left, blah, blah, blah. I hope that made some sense. So these all have 2 valence electrons, and the 2 dots can be on any 2 sides of the symbol. Okay, those are Lewis structures. Aufbau. We just said that group 1 and group 2 are the 2 groups in the S block. There's group 1, here's group 2, and you see that in their Aufbaus as well. So if we're doing an Aufbau for magnesium, we're going to have that core, it's got a neon core, and then in its 3s orbital, it's got 2 electrons. Just like in its Lewis structure, it's got 2 outside electrons. Okay, how about calcium? Same thing here. Calcium's got an argon core, and then in its outside s orbital, it's got 2 electrons. You may start to notice that like whatever the noble gas core is, doesn't super matter. It's gonna be a different size, but like kind of whatever really. The key is that the noble gas core is super strong and super stable. On a related note, we just said that the alkalis are really unstable. The alkaline earths are also unstable. They're not quite as unstable as the alkalis. The alkalis blow up on contact with water. The alkaline earths are stable enough that you can use them as fireworks, which, like, by the way, those blow up. But you have to be able to like structure the firework. Like the alkalis are so unstable you can't even put them into a firework before they blow up, whereas the alkaline earths like sit around long enough to get stuck into a firework and then blow up in the sky. But they still blow up. In lab, we frequently burn magnesium, which is like kind of wild because it's just like this like hot white kind of flame. That was not a good sound. If you know Mr. Leaf, he was once called to fight a fire where part of the information from dispatch was like, this garage has magnesium in it. And they were just like, what? Like, why? Like, that's not a good idea. And so, you know, in the middle of the night or whatever, he had to figure out how to deal with this metal. Here's magnesium that blows up, you know. It was gonna just destroy all of the structures nearby completely. But it takes a little bit of fire, it takes a little spark to ignite something like magnesium, whereas sodium, you wouldn't even have sodium in your garage because like it wouldn't be there, it would have blown up already. I actually have sodium in my lab. We typically, we not infrequently will burn sodium. I can definitely show you a video for that. And we might actually get to labs so I can show you like how I store it, because if I let it touch water, it will blow up. But if I keep it preserved in such a way that it is unable to touch water, it's like relatively stable in this other environment. So my clue is, think of a liquid that is repelled by water, does not touch water. It's a liquid that might come to your mind. Think like the other clue is salad dressing. So it's something in there that the sodium is stored in, and that's how it doesn't blow up. But as soon as I open that bottle, we move fast because crazy things happen. Okay, right. Okay, but back to the alkaline earths. These take a little spark to get them going, but then they also blow up. And also, just to finish this little thing, this is another thing that you probably, since you were a little kid, your family or somebody has been saying, eat your calcium, it's gonna make your bones strong, and it does lots of things. We talk about, actually in forensics, some of the things that calcium does. It has a lot to do with how your muscular structure works. So sodium is kind of the powerhouse of your neurons, calcium's kind of the powerhouse of your muscles, although that's super oversimplifying. But these are also, so these are both, I could have said this for both the alkalis and the alkaline earths, but they're both biologically active metals. There are a handful of biologically active metals in the transition metals, but they're few, far between, and like super wonky. The alkalis and alkaline earths are biologically active once they've lost these outside electrons and they've just got that really stable core. They kind of become messengers that run around all of your cells and like send messages. For example, all of your neurons work through this messenger, and your muscles contract through this messenger. Cool. All right. And you'll get tons of fun facts and uses and stuff from your student presentations. Let's keep ourselves rolling along. We are 2 groups and 20 minutes in, and let's just keep going. Group 3 is the transition metals. I usually give where they are located first, so let's do that. So here's helium, there's your P block, here's your S block, there's hydrogen. That is not correct, but I think you maybe hopefully kind of get the point. Your transition metals are here. This D block is the transition metals. Okay. You've been hearing about these for a while, like this name. The alkalis and alkaline earths might have been the first time you heard those names a second ago. You've probably been hearing this name a lot, which is great. Okay, so transition metals have Lewis structures. You will, I think in this virtual setting, I didn't do any Lewis structures because really your outside electrons of your transition metals, here's usually the big reveal. I don't know if I did a very good job of this given how weird last week was, and Aufbaus, and you probably hate Aufbaus by now. Good. Okay. But Aufbaus, sorry. I just said you hate it, now I'm doing another one. Aufbaus for things like, let's do iron, and we'll do it the core notation way. So the core inside of iron is, here's iron, zoop zoop, reverse typewriter, boop up to the noble gas in the line above. So can I put this on the page? I can. Okay, and we're going to go this way, back to the original point, boop up to the line above. Iron has a core of argon. Okay, so it's got an argon core. And after that argon core, over to here, we've got the 4s filled with 2 electrons. So the 4s has 2 electrons. The D's have a weird enough shape that they are smaller than you think they are. So like physically in space, this smaller orbital is inside of this larger orbital. Because your 3D is size 3, it's inside, like a stacking doll, it's like inside of this larger size 4s orbital, which is part of what give transition metals their properties. we're getting to iron. 1, 2, 3, 4, 5, 6. Okay. So iron's got 6 electrons and it's 3D. Okay, so your transition metals are structurally characterized by having outside electrons in their d orbitals. Now, another thing that we haven't gone into a lot of detail on, these kind of become similar energy levels. You start seeing light waves that are like smaller and closer to each other because the energy jumps between the S and the D just get really small. So they can trade electrons easier also. Where is it going with that? And it kind of gives them their properties. So transition metals are relatively stable, kind of because they can kind of like swoosh electrons between they've got more suborbitals to dump their electrons into because the D has 5 suborbitals. So your transition metals are relatively stable. They are super good, really good at sharing electrons. So, okay, really good at sharing electrons. What does that mean? When you think of metals, you're probably thinking of transition metals. So things like they conduct, heat and electricity. All of that has to do with sharing these electrons. They're just really good at giving and taking, and like, hey, you can borrow some of my electrons. I've got all these d suborbitals. Like, I can just hold on to some of yours for a while, or you can take some of mine. It's all good. They're really, for example, electricity is all about all these metal atoms basically just holding hands. So like, you give an electron to me, I give an electron to somebody else, it's all good. You know, like they've got this like electron flow. The technical term, ready? Okay, technical term for sharing electrons between transition metals, we think of these bonds and these metals as having a sea of electrons. Unlike your alkalis and alkaline earths who want to get rid of their electrons, they want to throw them off and be gone, be done, never see them again. And you'll see over on the other side of the table, we've got a lot of possession issues. We really want to take from anyone. In the transition metals, we've got this sea kind of going on. They're just really good at sharing. This is what makes them really stable. Also what makes them bendy. You don't think of iron as being bendy, but take your paper clip or your soda tab or whatever, like you bend metal all the time. I usually pitch it to the room of like, show me a metal that you're like probably have, like, I don't know, always say it this way, but like I could, like a metal that you've bent since you've been in this room today. You know, there's probably some, like the spiral binding on your notebook, that's metal, that's bendy. Unlike things that are super rigid and break if you try to bend them, there are molecular structures that are bendy also, but like wires, like your charging cable, your headphones, you just wound those up and put those in your pocket. Never mind, nobody uses, whatever. But that's a metal inside that you just bent. Okay, great. So they're really good at sharing their electrons. And I'll let the student group do some more like kind of fun stuff because there's tons of uses of these things. We'll not take your time right now going through all the uses. Okay, I think I'm going to put half of the groups in this video and then half in the next video. Let's do group 4. Group 4 is another metallic group, and group 4 is the inner transition metals. Oh, I did the... messed up my structure. I usually put my table over here, my name over there. Okay, I'm not going to redo this. Great, I'm going to put the table underneath though. Okay, so the inner transition metals are down here. So, okay, there's your general table silhouette or whatever. Your inner transition metals are the F block. So you've done tons of Aufbaus by now. And your inner transition metals are your F block. We could print them in the middle. That would get us a different aesthetic picture of our periodic table. They often get printed underneath to print on an 8.5 by 11 sheet of paper. Okay, let's do properties first, just to mix it up a little. Inner transition metals are weird. You're like, good, that doesn't sound very scientific. They're characterized by these F orbitals. Okay, so much for properties. Aufbaus. Let's do a reasonably not terrible. I was gonna say let's do a reasonably not terrible Aufbau, but once you've got this core notation, nothing is that weird. We can even do a horrible looking one. I don't even know how to say this one. Let's do that one. Disporcium. I don't think I've really given that one much thought ever. Okay. Oh, but it's all 66. Look at that. Okay. dy. This seems appropriate after all the terrible Aufbaus we've done. Okay, so let's do Disporcium. And we're going to find its noble gas core, which is going to make it tolerable, or at least more tolerable. Okay, reverse typewriter. So bank up to row 6. And then find the noble gas above it. Okay, so above it, we've got the noble gas of xenon. Cool. You'll notice that this noble gas is written the same, basically as stable as the other ones. Some of these really big floppy noble gases, xenon's huge. It's got a full 5p. Xenon's a little bit more flexible than the other noble gases, but it's still a core. It's still basically impervious to anything. Okay, so there's your noble gas core. Xenon will bind with fluorine, which makes it like very risque for the noble gases. Okay, so there's your noble gas core. We're gonna forward typewriter to row 6. Here's row 6. You've got your 6s filled with 2 electrons. 1, 2. Okay, take yourself down to your F block, because what we're doing here, inner transition metals are all in the F block. Okay, so down we go, 55, 56, 57, and we're going to Disporcium. So off we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so Disporcium has 10 electrons in its 4F, which is like a lot of electrons. Great. Your F orbitals have 7 suborbitals that are all super similar in energy level. These 10 in the F and these 2 in the S are all pretty close in energy levels, and it's you know, they're also very good at sharing, kind of like the transition metals, but they've just got weird shapes going on, and they become really good at, I imagine they're also really good at conducting heat and electricity. They're probably amazing at conducting heat and electricity. But the other like unique property that they've got with all these 7 suborbitals in the F is they can get 7 electrons spinning independently from any, like, in the same direction. They're really good at being, let's take out at, really good magnets. So any application across Earth, space, medicine, anything, if you need a strong magnet, go talk to the inner transition metals, because they've got more power than anybody else in the magnetic spin realm. this is like the breaking technology research, new tech research. Because of these magnetic properties, that's where you're going to look to figure out how to make your tech go faster, stronger, etc. Piggybacking on your transition metals, they also kind of have a sea of electrons going on, but an even wider, broader sea than you're able to achieve with merely the 5D suborbitals. Okay, cool. I'm going to end this one here. I'm going to do the next 4 groups in the next one.